Here, we're asked to find the probability of the quadratic polynomial where the coefficients a and b are determined by drawing i.i.d. uniform random variables. And this has at least one real root, this coefficient. So in the quadratic formula, by the polynomial root, this polynomial has a real root if and only if this condition is fulfilled. So what does this mean? It looks quite convoluted. So let's just start by writing down what we know about the quadratic formula. So we know that basically what this was given to us here, but we can also figure out the real root by the very well-known quadratic formula, which I'm just going to cite here, like so. Basically, we're taking the following coefficients minus 4ac. So this is the quadratic where it becomes quite clear to us where we are, where this is larger than 0 comes from, right? So we have to take the root of something positive. So if minus 4c is larger than b squared, we're entering the negative domain, and this will be invalid in terms of real numbers at least. So now we are understanding where this condition comes from. And also, just to go back to the information given to us, a and b are drawn uniform. So at certain occasions, I mean, for example, when b happens to be 0, very close to 0, and where a is close to 1, we will have this term here becoming negative and thus invalid. So that's all good. Let's try to draw this to visualize it to see what is really happening here. So we'll draw the B line and then the A line there. So that's A, that's B. And we know that they are operating on a support from 0 to 1 for B, 0 to 1 for A. So let's draw this like that. So this is the support. This is where A and B can operate. And let's draw a line visualizing where this condition is valid versus invalid. And that we do by taking B, this condition, B squared, minus 4ac is larger than equal to 0. Now we're also given that we know that from this quadratic polynomial c is equal to 1. So I'm going to just write 1 here. Well, basically just remove it. So that's 1 times 1, like so. Now we try to solve for b, well, basically to see how we can, what information we can get from this line here. So b is now 2 square root of a. Okay, well, that's good. So we're now approaching some additional information that we will going to get from this little function here. So when will this function, this curve, hit b equal 1? Where is that? Well, let's figure that out by writing if b equals to 1, then b equals to 1, then we have 1 like the following to a. So I'm going to check basically where what a is when b is equal to 1, and that is then a half a square 2. So that's this region here. Okay, that's useful information. So let's plot this little function here. So we have 1, 4, 1, 4, and then we have, and then we know that this function also starts at 0, so it will start here, and it will hit, let's see, it will hit 1, 4, so it will go something like that. And in fact, if you take up your graph plotter, you will see that it will be looking something like so. So this is when b equals to root a, this function here. So that's good. Okay, so we know that it starts at 0 and it hits a at 1/4. Now, how do we use this information? Well, essentially, what this is saying to us, this function here, is that as long as we are in a region larger than this function, so it's here, we will be getting real roots that are valid. So let's do that. Let's just put this in green. So in this region we have valid roots. That's useful, and all the remainder of this region will produce roots that are invalid. All right, so now we want to figure out the area of this valid region. So that's good. Let's start by then figuring out what that is. Well, the probability of the valid region, so we can basically just start with saying the b squared minus 4a has to be larger than 0. And this is basically the probability of this event, this condition, being fulfilled. It's the same thing as the probability of b squared larger than 4a, and that's the same thing. I'm just going to swap this to make it a little more common to the eye, like that. And now we have a double integral that we're going to solve for, where a is in the region of interest. And now look at this function. This is the inverse of this function here. So we're just basically flipping the axis here. Okay, so this integral now, you have to be a little bit careful about what region, the limits of the region. And let's start by looking at the inner part. We know that this function starts at 0 and it goes up to either it will hit the limit of this function, hit the function, or the limits of our support, which is where b equals 1, and therefore we have to rewrite this as the minimum of 1 or b squared divided by 4. Okay, that's the inner limit, and this is now integrating in the a region, and the outer limit. What is the outer limit? Well, now we're integrating over the b region, and this region is the full support of b. So that we write as 0 to 1. Great. And the taking that over the joint A, B. But we know also that the joint PDF are uniforms and they're i.i.d, so this will be 1 times 1. All right. And so let's now move on to figure out where basically this condition will be unfulfilled, or basically another way of asking, over the region 0 to 1 in the b direction, will there be ever an occasion where this min equals 1 comes into play? Well, not really, because we are moving in this direction, and from 0 to 1 we will never be past this region. So this is the same thing as just writing 0 to b squared 4. Like that. dA, dB, and we integrate that inner over a, so that's just a, from 0 to b squared. It's 4 dB, and that will be just b to 4, because we'll be taking negative and subtracting off 0, and so here we have b squared times 4, 1 dB, and that is now b3, this is 1/4 times 1/3 and over 1/3, and this will be 1/12. That is indeed what probability of getting a real root. Now, one thing about this problem which is interesting is that you could think about it moving in the other direction. You could take we did now, which was the most straightforward thing, to integrate over this region here. But we could take the complement and integrate over that region. And although it is a bit more work for this problem, I would like to do it just to show you how useful it is, and basically double check whether we get the same answer by integrating first over the over the B region here. So basically integrating in this direction here. Okay, so this first thing was integration. So let's call this A first. So basically we integrated over D A first here. And let me copy this one just to not have to scroll all the time. Copy, paste, put it here, and then we're going to integrate. So do B first, right? And then this means basically we have to start with dB first. All right. We start in the exact same point. We take this, copy this, like that. And now, because we want to integrate over the B region, we'll be flipping the inequality. We're taking the complement here. So B squared minus 4a. Now we flip this like so, and we continue on, and we'll have b squared now being less than or equal to 4a. Probability of b root squaring the whole thing, so we'll have a 2 here and then square over a. Okay, and this is now the same curve but moving in the direction that I first started to talk about, so it's natural in that way. Okay, so what does this probability mean? Now we're still in the double integral mode because we have two random variables, and what are we doing here? Well, we're basically doing the same operation but moving in the other direction. So we have all the b's sort of slices lined up like so, and here we think in the same way, basically asking that we put the inner integral. It starts from 0 because we are starting from here, and it again we have to be careful about the support, so we write the minimum of 1 and 2 square root of a here, like so. And then we take the density f a b. Whoops, let's write small letters like so, integrating over the b region, and then we do the a region as the outer integral, and that goes from 0 to 1 over the whole support of a. Okay, so that's good. Let's try to open up this minimum thing here, because we do have a random variable. We have to be extra careful about what region we're integrating over. And we can immediately see that once we pass 1/4 in the a region, we will be out of the support if we don't account for so we do have to account for the fact that once we are out of the support 1/4, that we need to correct for the limits of the integral in that direction. And so one way to do this is to split the inner integral. So this is the outer integral, and then the inner integral we split into from the region 0 to 1/4. So this is the region moving up to here. So we have almost like a triangle. It's not really a triangle because we have this curve here. And so we do then, well, so I did two things. So I actually split it up the outer integral. So this is, my bad, we should not write this out like so, because we're splitting up the whole integral into pieces. So first we're going to integrate over 0 to 1/4. This is the outer integral. And in that case, we are safe that we will be never out of support. Okay, so then we can just basically write 2 square root of a. And then we have 1 d b d a. And then though we have the remainder of the support, and that is when the outer integral goes from 1/4 to 1. So we're 1/4 to 1. That's what we're doing. And now we do have a rectangle shaped thing here. And that we can write as 0 to so 0 to 1, because we are in the region of the b region, the b direction here. So we have a square. So this will be fairly straightforward. 1 d b d a. Okay, so now it's a matter of simply, let me just do this a little nicer, 0 to 1/4, and this inner thing here will be b 0 to square a dA, and this term here will be b 0 to 1, and then we integrate from 1/4 to 1 dA. Okay, and so continue on. 0, 1/4. It's important to write out the parentheses here. I'm going to write this as 1 squared like so, dA, and this thing in here doesn't depend on A anymore. So here we'll have basically do this on the side just to calculate a little quicker. So this thing here will be we have 1/4 1, and then we have, so that's a 1 in here once we have set B to 1 again. So this will be then A let me just do the following. So we have, just doing this a little quicker, so we have 1 here, and we take the integral of 1, that will be A, because we're doing it in the A direction. And we then have the region of integration is like so. So this will be 3/4. Right, so we have 3/4 here. Okay, that's good. So we're done with that. Let's just focus on this part here. And this will be continuing on. This will be then by taking the integral of this, we add 1 to this, and so we end up having 3 divided by 2. This is the power 2a, 3 divided by 2. And then we have to divide by the same amount, so we have 2 here, and then we have 2/3 to cancel that out, and we're doing it over the region 0, 1/4. Okay, plus 3/4. So it's a little involved, as you can see, but still, this is a nice way to verify whether the first answer was correct. And by simplifying this further, we get let's see, just do this a little quicker. We see that we get in the end, so this will be 1 minus, and then we get 2 squared. After simplifying this, I'm not going to and opening up the parentheses like that. I'm not going to do all the details. These will be just algebra at that point. 2/3, and then 1 minus will be 2, so 1/6, right? So canceling out 2's there, we have a 3 times 2, right, minus 3/4, and then making sure that we write all of these on the same denominator. We end up having 3 minus 2 divided by 12, and that is indeed 1/12. So I skipped the little parts here in the calculation, but you can basically verify that this will end up being 1/12. And that's a nice reassurance that we have gotten the same answer by looking at the full probability and integrating first over this region, and then basically taking 1 minus the complement of that region.